예, 뭐 시작을 하지.
네.
So we have a series of lectures today. Not sure that if the second colleague is going to lecture or review, but very happy to have two talks today. And the first talk will be more lecture. Particularly, we want to learn about the recent issues on H0 tension. So, please welcome Donghui.
Okay, thank you very much. And this is the lecture upon request from Jeong. So I'll talk about this review paper by Kamyakovsky and Rees. They are two Johns Hopkins faculty members. They are colleagues and they wrote the paper together. And Mark Kamyakovsky is a theoretical physicist. And Adam Rees, as you know, is astronomers. They work together to write this fascinating review titled as the Hubble tension and early dark energy. So in the introduction, they started from some fascinating story about Hubble tension. There are history of Hubble tensions. The oldest Hubble tension is from the value of Hubble parameter that is measured by Hubble. So the first Hubble tension historically, I think I want to tell you about this because that's interesting. So first H0 tension was already there in Hubble's 1929 paper. So there, if you look at the slope of this relationship between the distance and the redshift, so Hubble constant value is about 500 kilometer per second per megaparsec, which is pretty high, right? And if you think about all galaxies were in one point and then start to move away from each other with this velocity per 1 megaparsec, that gives us this time scale T naught, which is 1 over H naught. That is about 2 gigayears. That was 1929. Back to the old days, they already knew that age of Earth is about 4.5 gigayears. So that was the Hubble tension, the very first Hubble tension. And this Hubble tension was caused by many factors, but one of the important factors is that when Hubble calibrated the distance to the galaxies, he used one category of Cepheid variables, regardless of their population. But these days we know that there are POP1 and POP2 Cepheids, and then distinguishing between those two actually brings the value of 500 down to anywhere between 100 and 50. You know the story about this too, right? The 100 was advocated by Butler and his company, and 50 is by Sandys and his company, and they never agree with each other. One thing that they agree is it cannot be 75. That's a fun thing that now we have something close to 75. And second Hubble tension, the history that they mentioned in the paper is after Hubble Key project. Well, it's like historically it's before Hubble Key project, but then they mentioned this thing because this is a project settled the value of Hubble constant around 72. So that is one of the key project of Hubble Space Telescope. That's why it's called Hubble Key Project. That's Wendy Friedman is early 2000 result. But then combine this thing with omega matter equal 1, which is preferred by theoretical reason because of inflation. Universe is flat and is filled by matter because, well, this is 2000, but this second tension is around 1990. Okay, but then if omega matter is 1, if the matter encloses the universe, then we know the expansion rho is A is proportional to scale factor to 2/3. That gives us E naught. That is 2/3 H naught, which is about 9.3 gigayears. So that is the age of universe. We compute it by assuming that universe is filled with matter and Hubble parameter measured from the HST. And the tension here being that this one is less than the age we measure from the globular cluster by tracing the HR diagram. Right, so HR diagram has a turnaround point from which we can compute the age. But then so this first Hubble tension was solved by realizing that there is two populations of Z phase. And the second Hubble tension is resolved by cosmic acceleration. And that was measured like late 90s by second author of this review. But generically, you can think of this way that for a given Hubble constant, if you include cosmic acceleration, that will extend the age. Okay, that's a very generic statement. You can think of it this way: so it's a function of t and a of t. By knowing the Hubble parameter, what you know is at current time t0 and some t, we know the slope of this curve. Right? That's given by h naught. Right? Without acceleration, all the past history, the expanding speed must be slower than h naught. And then you have something like this. But if you allow some acceleration, this curve can be concave. So what you do is for a given slope, you can do like this. Right? So generically, having acceleration will extend the age. Because in this always decelerating model, that is age of universe. And this deceleration, then acceleration model, and that is age of universe. Okay. And then third Hubble tension, their point here is that we had Hubble tension before in the history of cosmology, and each time we raise the Hubble tension, that is resolved by deepening our understanding of astrophysics or fundamental physics. So they surmise that this Hubble tension that we are facing right now may also lead us to some discovery in astrophysics or cosmology. So that was their kind of optimistic view about the Hubble tension. So that's the introduction.
We were in another room.
Oh, sorry. Any questions? You can read. That's all I wrote. We're talking about the historical introductions. We didn't miss much. Okay? Cool. So Hubble tension, what we have right now, we are facing right now, is a tension between the Hubble parameter measurement and that we have done in two different methods. So first category of Hubble tension is H naught from early measurement. I'll specify what early means. And these early measurements include CMB, causing microwave background. I think I'll give you more details of how this thing works later. And baryon acoustic oscillation. Okay. And these CMB and baryon acoustic oscillation, they both rely on the fact that the early universe we have acoustic oscillation of baryon photon plasma. But then there's third one, which is not related to that, but related to somehow the cosmology is called the matter radiation equality. These three observables point us to the value of Hubble parameter 67.4 plus minus 0.5 kilometer per second per see 67.4, but then this error bar is 0.5 now, right? That's amazing.
Underestimation.
Maybe. And the late measurement this includes essentially all local measurement, I should define local as well. That gives us, I think, they are quoting the representative value, so 73.0 plus minus 1.0 per second. And local measurements here include all we know and all we learn and love in our astro classes. Includes, I mean, this basically includes something like a distance ladder. But the very nearby universe, we always use geometry. That means parallax. Okay, but geometry cannot go too far because our solar system radius is only about 500 light seconds, so we cannot measure parallax down to very far away. But then there are some objects that we know for which we can compute the absolute luminosity or absolute size. And then they are the intermediate distance indicator. One of the most famous one is Cepheid. And there are other variables that's called the Miras. And there's some group of stars called the red giant branch stars, but then they have tip at the red giant branch called TRGB, tip of the red giant branch. And then we have famous major star, NGC 4258. I think that's the right number. I don't know. Somehow that sticks my brain. I'm not sure about the name, so let's just say it's major. Right. So important thing is that for some stars, we have overlapping between geometric measurement and Cepheid measurement. And we can calibrate this distance luminosity relationship, or Miras and TRGB. Major is too far away, so I think to use major, we have to first use geometry and then Cepheid and then major. But there are a couple of letters. And then eventually, what we want to use is the type 1A supernova, which is known to be very well regularized standard candle. So eventually, what you want to use is this to measure H0. Okay. Questions? It's weird, right? H0. What is H0? That is expanding speed right now, at this moment. But then to measure H0, we cannot use geometry. We cannot use Cepheid. We cannot use all those local things. We have to go far away.
So in the calibration of the supernova depends on the geometry and some media data.
Yeah, that's right. Yeah, it's all based upon the distance ladder. Right? Ladder means that if you are to climb up, you have to go one step.
All the data about depends on the data.
Yes, that's right. The reason is because let me define. There's a mathematically precise definition of H0. So when redshift goes to 0, this is a relationship that Hubble discovered. H0 times D. For local galaxies, we measure the redshift, the spectral shift, because we know where the spectral features should appear from the, say, quantum mechanics. And then we measure distance by any of the method, then you can have H0. But inconvenient truth is that the redshift that we measure is not just Hubble flow, right? Galaxies are not just following Hubble flow, they are moving. It's called the peculiar velocity. For some of us, like me and Changbom and Alexandra, peculiar velocity is a signal. But for H0 measurement, peculiar velocity is a noise. And then real spectral shift, I think that's G observed, is the Z, let's say Hubble flow, plus peculiar velocity normalized by H. I think it's just C. Let's see. Okay. So we cannot, because we don't know, we cannot define a rest observer around the spider's observation. But what you're doing is instead, we extend our space of observation. So beyond this limit linear regime, we have to extend the equation to have the real equation for distance as a function of z. That is cg over h naught. So h naught here is acting as an absolute normalization. And of course, we can expand it as a power of redshift. 1 plus q0 over 2 c. And 1 plus q0 plus q0 squared over 2. And this is famous equation that you can find anywhere in cosmology. Okay. So as you can see here, this term h naught is multiplied to the whole dependencies. So when Adam Rees analyzed the supernovae data, therefore he didn't care about h naught. Okay. What he did was just focusing on the shape, the redshift evolution shape. It's called the uncalibrated or the relative distance scale, because then by looking at the quadratic or the cubic and quadratic and linear, we can fit this Q0 so-called the deceleration parameter and J0 so-called the jerk parameter. That's what gives Adam Rees the Nobel Prize. But now that we are considering the absolute normalization, he started to care more about h naught. So for the relative calibration, in fact, you don't need this nor that. You can just use supernovae, right? You don't need to know the overall normalization. You just have to know how they scale as a function of redshift, right? But then to know the h naught, you have to know this overall coefficient. Then you have to rely on the full distance ladder. Okay. And then we have very nice calibration point for connecting the geometrical measure to cepheid. So just to give you some sense of how accurately we can measure the absolute distance. So from the major NGC 4258, that is the system with the water major, because we have a major line. So major line is well defined, and this water major line is edge on, right? So we can have the Keplerian motion, because some direction is moving far away from us and moving close to us, right? That you can solve the binary motion, like the Keplerian motion, to solve for the distance. And then we have some cepheid variable in this galaxy. From there, we can calibrate distance down to 1.5%. That's pretty impressive. And with the recent satellite Gaia parallax of Milky Way stars, we can calibrate distances down to 1%. And in the LMC, we have a couple of eclipting binaries. You know, if you have binaries and they're eclipting, then we can solve for the binary parameters. That's really nice. So LMC binary. We also measure distance down to 1.2%. That's fairly impressive set of achievement using the astronomical observation. And to get an overlap between cepheid and type 1a supernovae, they use 42 supernovae in the local 40 megaparsec. That's very nice. Supernovae happens once every century per galaxy. Okay, that's very rare. But then it's kind of amazing that we can detect 42 supernovae in the 40 megaparsec boundary. The important thing is that they only use these 42 supernovae for the calibration. they never use them for measuring H naught. Because measuring H naught, they have tons of supernovae between, say, D40, D greater than 100 megaparsec. So these are the supernovae they use to measure H naught, right? Because peculiar velocity of galaxies are typically, say, order, I don't know, to be safe, is less than 1,000 kilometers per second. Okay? And then you can, only after you go further away beyond 100 megaparsec, your spectral shift due to Hubble flow is negligible compared to 1,000 kilometers per second peculiar velocity. So that's, I think, something that I learned. I didn't know that actually before reading this. I thought that they all fit all parameters at once, but they didn't use this. Yeah, they only use high redshift supernovae for calibrating H naught, and the reason was the peculiar velocity. Questions? Yeah.
The 42 supernovae are used for what? I missed that.
That's the calibrate the distant ladder. The distant ladder, you have to have overlapping geometry and can separate. Okay. They separate and supernovae. Then after that, they use them as data.
Yeah.
You pick the normalization. So it seems to me that, I don't know, I'm not the right person to judge, but their local measurements seem to be quite robust. And it will only get improved. I was thinking about dust effect, but then they're talking about recent JWST observation, where they have recalibrated their Cepheid with the infrared, which is less affected by dust, and it's consistent broadly with their previous research. So, okay. This value seems to be quite robust. 73. Okay. I don't know. And they also said, oh, people talk about unknown systematics, but unknown systematics by definition cannot be tested. We don't know what to do. But yeah, 1.0, that always bothers me, because after all of this, rather thing is all calibration. Right? Then can we attach like 1/73, like a little bit better than 1% error bar from this calibration?
Constraint H naught.
Yeah.
Then we need to go through all these distance ladder.
Yeah, right.
So,
But then dark energy, we don't need those. We just can do it without all the absolute calibration.
right, I mean, that depends on this redshift dependence.
Right, yes.
But to constrain amplitude,
Right.
need to go through. So all the uncertainties in these empirical relations will be accumulated.
Yes. Right, that's that. And then in this review paper, I think Adam Rees also did it for his science paper as well. They have a combination of various different assumptions that they use, and they showed all the different results that they got. So if you can see it, that's 71, 72, 73, 74. So all the red dots are the various different assumptions, how they affect their value of H naught. It never goes below 72. Just one case out of like 60 some cases. So it seems that local measurement based upon distant ladder strongly prefer H naught that's larger than 71. Which is in tension, according to their evaluation, 5 sigma tension, more than 5 sigma tension with the value based upon the cosmology theory or cosmological observation. Okay? Good. I mean, that paper include all the more details about how a late time measurement was done and what kind of possible systematics that we can expect. So if you're interested, please read.
Before you erase, if we suspect the error bar would be underestimated, what would be the most suspicious? David, do you have any? So one thing David suspects is that as we see galaxies further away, I mean, the galaxies which contain Cepheid away, there will be some blending, okay, of the brightness of Cepheid because they are typically in crowded field. They are
I
like
see.
one star, so they typically in the disk. So
Right.
they suffer from, as you said, confusion with other stars, and also suffer from more extinction as well.
Right.
Well, they must have paid attention to this.
Yes, because I mean, then you, as you said, yeah, it is a ladder, right? So this is one step, but then you combine with others. Eventually, as you said, all the way to type 1a supernovae, and everything seems pretty much consistent. So that's why they claim that the aerographs are well under control.
Right. So I think for the question, yeah. Sobi, that's Sobi.
Yeah. So you mentioned that they use like for measuring H naught, they only use the high redshift supernovae, right? Beyond 100 megaparsec, because you want the peculiar velocity to be small in comparison to the. But what about the calibration of supernovae using Cepheids? That is done within 40 megaparsec, right?
Right.
So is the peculiar velocity not important there for the calibration?
I don't know. Yeah, it's true that peculiar velocity. No, okay, and that's true. But I think if they didn't use redshift information at all for the letter, right? For the letters, what they use is they match the distance modulus for geometrical measurement and separates and then supernovae. And then redshift is only added at the last step. They only attach redshift at the last step at the very high redshift supernovae. But for the low redshift object, they just measure distances. Does that make sense?
I see.
If you have their paper, there's a plot, figure 3 of the paper that explains how distance ladder works. We have sepate and the geometry measurement in the very first square, geometry and sepate and supernovae and then redshift. So peculiar velocity in fact for the lower ladder of the lower rung of the distance ladder. Yeah.
Okay, thank you.
If I add one more comment, so actually one thing that I suspected is probably the point that Professor Young Lee and Yonsei University made. So the way they calibrate, the way they determine the absolute magnitude of the type 1a supernovae, because it requires, lots of the treatment of the light curves data. So probably in that, if Young's point is correct in the sense that there are two types of type 1a supernovae, the reliability of type 1a supernovae, then probably there could be some the way to reduce at least the value itself, not the uncertainty.
Yeah, could be. I think that's the point of, as far as I understand, ongoing debate. And I think in this paper they also mentioned this effect of metallicity and age. But seems like they said, just in passing, they said, oh, they tested it and didn't make huge difference. But I don't know if that statement is well backed up.
Okay.
I also want to add one thing. So even at the distance of 100 megaparsec, the peculiar velocity effect can be a few percent. So it's not completely negligible.
Yes.
100 megaparsec actually is 70 h to the minus of megaparsec. Okay.
Right.
And if the peculiar velocity is 500 kilometers per second, that's going to be 5 megaparsec, 5 h2 megaparsec.
Right.
So that's almost 10%.
True.
So,
But I mean, it's the starting point, and they went all the way to like gigaparsec and beyond.
yeah, they go further away.
Right. I think this borderline is a little bit funny. Okay, so that's about. As you can see, we can have some discussion point for the late time measurement because this is based upon the calibration. There are many ways that this could go wrong. Right. On the other hand, let me tell you about the early measurement. This is based upon the concordance cosmology theory that I have spent all my career with, and then it doesn't have much room to change. So let me tell you about that. And it's all I mean, the robustness of this number came from the robustness of CMB measurement, except for the foreground. I know that Changgom is worrying about the foreground of CMB. Could have some impact. And unlike the local distance measure, by looking at how CMB measures the H0, we can even guess what could be the possible resolution for this Hubble tension, because this is based upon the first principle theory. I even have an equation for H0. Okay? So, CMB power, the observational input here is CMB power spectrum, CMB say temperature, and polarization power spectrum. In the plain vanilla lambda CDM model, we can fit these these zillions of data points by only using the 6-parameter plain vanilla lambda CDM. And those 6 parameters are AS, that is the amplitude of primordial density fluctuation, and S, that's the tilt of the primordial density fluctuation, and omega B, that is the baryon density at present time, and omega M, that is the matter density at present time, and our favorite H, Hubble parameter, present time, and tau, that is optical depth. Optical depth means that how much CMB photon, what's the fraction of CMB photon that we observe now, which is primordial. That is 1 minus tau. These values we measure very, very precisely. Among all those values, I mean, there are some derivative, I mean, these are the derived parameters. And then primary observable, one of the primary observable that we measure from CMB is called the theta S. That is a sound horizon scale, the angle subtended by the sound horizon scale. Okay? That's defined by sound horizon distance at redshift 1000, with decoupling the last scattering time, over the angular diameter distance. It's called GLS. LS here means that last scattering of CMB photons, for the bulk of CMB photons. Okay? And we measure this number. I will write the number because I just want to impress you. 0.041, sorry. 4109 plus minus. I already wrote 6 digits. Why? Because error bar is so small. 0.0003. This is the value that we measured, about 0.6 degree. Look at the error bar, right? We cannot change this number because that number is encoded in the WMAP data, Planck data, right? This is just written on the stone, okay? Good. And this number we can compute with 2 numbers, angular diameter distance and then sound speed, and the sound horizon. What is sound horizon? Sound horizon is the distance that the baryon photon plasma propagate from Big Bang up until the last scattering time. So we can integrate sound horizon by from t equals 0 to t equal t last scattering. We multiply the sound speed times physical time, but then we want to compute the co-moving horizon, so we divide by scale factor. Good. Speed, time over scale is familiar. And what's the sound speed? Sound speed, that is adiabatic sound speed, is partial p, partial rho, when that is adiabatically expanding. Right? And then we know how p is related to density. So that is 1/3. Then this p and rho are the, say, baryon photon plasma, I call B gamma. P, B gamma. I mean, baryon doesn't contribute much because photon already move so fast. So that is 1/3 of rho photon times c squared. Right? And then rho photon in the adiabatic expansion phase is proportional to scale factor to minus 4 power, and 0 is present value. The density, B gamma, is simply baryon plus gamma. Right. Which is rho baryon now, A to negative 3, rho gamma now, A to negative 4. Right. So here, zeros are the parameter that we can measure, right? And then when universe change adiabatically, the only variable that you can vary is scale factor. Right? So these partial derivative you can translate to the derivative with respect to A. Of gamma. Okay? If you do that, you get the famous equation of C squared. Famous result that is C squared over 3, 1 plus 3 rho baryon for gamma. Okay. And then we call this R. So that is C squared over 3, 1 plus R, which is function of A. Right. Okay. Then plug in here. I'll just write this, and then I want to use the redshift as a variable, so I can say that is redshift z last scattering to infinity, because t equals 0 is redshift infinity, right? And CS is that, so c is z over square root of 3, 1 plus r times h. So that is the sound horizon size. That's one part that determines theta s. Good. It looks familiar, right? You've seen this before. Okay. So sound wave propagate this much distance, but then this h of z you can further expand using the Friedman equation. So I think in this paper they use the Friedman equation for flat universe, where the 3h squared is equating with beta g c4 times. Okay. Right. Yes. Oh. Let me just write down. That is c and square root of 3, and then I rewrite this as HLS, and so all I write here will wind up to be important. So dz, so you integrate square root of 1 plus r and rho of z over rho ls. Good. And then rho of z here at only on that is between redshift last t equals 0 to t last scattering. So what contribute to rho of z here is the matter and radiation in standard cosmological mode. No lambda, nothing else. It all, so RS only depends on the primordial physics. What happens between Big Bang up until last scattering surface. On the other hand, d of a is same integral. Then now we have h naught instead of HLS, h of last scattering surface. And from redshift 0 to redshift ZLS, dz over, I'll write the same notation, rho z over rho 0, 1/2. So they wrote this way because they want to emphasize the effect of energy density early on and later than the last scattering surface on h naught. Good. So now we have theta s, which is our golden standard. We know the number in terms of RS and dA, and those are all written in terms of known function. Hubble constant, R and rho, right? And then if you can combine these three pieces, then finally we can write down the expression for H naught. Okay. Good. Still have 20 minutes.
Good. So
Yeah.
So it seems one way to change RS,
Mhm.
okay, is to change rho of Z relation.
Yes.
Okay. So, but that's the rho of G relation before decoupling.
Yes. Yes.
So that's why
That's why. Yes.
early
Yes.
dark energy comes in.
Precisely. Yes. Yeah. That's where I mean, that's the direction that I'll go. They went. Cool. So combine all those equations. Now I think I'll write down one equation that is most important today, which is H naught on the left hand side is square root of 3 coming from the square root of 3 of the photon sound speed and HLS times theta S. That's our number, right? And then we have ratio between integral from late time integral that came from the angular diameter distance the early time integral that came from the sound horizon scale. So if you are to do some theoretical modeling of Hubble tension, that's the master equation that you have to consider. This one is right. And then let me spell out a little bit for how these are related. So HLS is 100 kilometer second per megaparsec times WR square root 1 plus ZLS squared and square root of 1 plus omega m omega r. Good. So HLS, that has this expression. Omega r here is small omega r is large omega r times h squared. Okay, so that r here is different from gamma. Okay, I'll tell you, right, gamma. And r here is including neutrino and photon. Because this three-dimensional equation take into account all radiation component you must include the photon as well as neutrino as well as photon. And here omega meter, we measure from CMB the height and the height of the peak, right? That's primary measurement of it. 0.142 plus minus 0.001. And omega radiation, we have an expression for this 7/8. So this one is a contribution from the radiation. And that is usual way of parameterizing this quantity. Let me explain after I write this. So that is a total radiation density. That is related to the photon density. And that obviously one is coming from photon. The other one is coming from the neutrinos. Okay. 7/8 coming from the fact that neutrinos are fermion, photons are boson, and 4/11, that is the 4/11 to 1/3. That's the ratio between CMB temperature to neutrino temperature. And we have force because the energy density is proportional to 4 power of temperature. And an effective, that is the effective number of neutrinos species, not 3. That is 3.046. That's just a glitch in the theory. We have three families of neutrinos, but the fact that we have 0.046 is because this whole thing came about because we have electron-positron pair annihilation happens earlier than neutrino decoupling, but then at the time of neutron decoupling, there are some electron and positron still remains to give some entropy to neutrinos. So it's not shortcut. That's what it's coming. But then there's omega gamma that we know very well because CMB is a black body with 2.7 Kelvin. Right? If you know the temperature of CMB, you can compute the energy density of CMB very well. Right? So this is as accurate as how that is accurate as the 2.7 Kelvin. 2.726 Kelvin. Okay? Is that accurate? Right. So we have, I talked about omega R, omega matter, yeah. And Z, logical and surface, this also depends on omega M and omega baryon, because it's all about how fast the universe is expanding compared to how strong your CMB photon was coupled to the baryon. Because you know the CMB temperature, or the other parameters are how fast the universe expands, that's omega matter, and how much baryon is available to interact with the photon, that's omega matter. So that's this. Yeah. Oh, R. I didn't write R. So R, oh no, I thought that. R was 3 rho B over 4 rho gamma, 0 times A, right? So that is 3 times omega B and 4 times omega gamma times A. And again, oh, and this one, omega B, we know also very precisely, that's 0.0224 plus minus 0.0001. I'm writing these ridiculous numbers because I just want to emphasize how hard it is to change this and still be consistent with CMB, right? Because these numbers with this ridiculous accuracy, those are all from CMB. So if you change this number a little bit beyond this tolerated number, then you screw up the CMB. All right. Good. Now, let's think about how to make this H naught. And then this H naught, if you include this face value, central value, right? And then you get 68 plus minus 0.5. Right. So then the game that you can play is, okay, I want to raise this thing. What are the possibilities? And this one, can I do it? Yes, because if you look at this, HLS contains all these things, but then we have omega radiation and omega radiation. Can you change omega radiation? Yes, because you can change N effective. And this ridiculous number of 3.046, that came from the particle theory, but then we may have other relativistic all species, right? Whenever you have some light particle moving so fast, and it can be included there. You can have some dark radiation, for example. Then this should be there. And if you include an effective, then you'll raise this, right? Omega R. Then you raise HLS. And if you raise HLS, fixing everything else, then you raise H naught. That's why people say, okay, if I increase N effective, you can resolve, or you can make the Hubble tension milder because you can increase H naught. Okay, that's one thing. Another thing is, what about including some late time solution? So this is early time. That's late time. So late time solution is proportional to this integral. With lambda CDM, you get 68. What if we decrease this denominator? Then you can increase this whole piece. How do we decrease this denominator? Because we know that this rho of Z, this contains matter, radiation, and lambda. For all of them, we know how they scale with ratio, or the scale factor, and A to 0. So for a given omega matter right now, omega radiation right now, omega lambda right now, we know how they scale. But one thing that you can play with is lambda, because that's dark energy, means that we don't know what they are. So instead, what I can plug dE and have rho d instead of rho lambda, and then I can have the evolution of a to minus 3, 1 plus w. Okay. What we want to do, we want to make this whole integral larger. How do we do it? We want to make the denominator smaller. So for fixed rho 0, if we are to make this thing smaller, that means that dark energy was relatively less important early on to reach the same density. Right? If you are to do it, what you have to do is you have to lower W less than minus 1. Okay? So H naught is increasing. There are two ways. First one is N effective. Effective. You increase N effective, then you increase H naught, or you decrease W, then you increase H naught. Those are the two solutions that you can think of. And that's, I think, when people talk about the H naught tension in terms of cosmological parameters, they are talking usually about this. Maybe we've seen this last week when Leila gave a talk.
So can we consider both at the same time? Can we consider both solutions at the same time?
Oh, sure, yes, yeah, of course. Yeah.
So,
I mean, because people do not like this idea, right? This phantom. It violates something called a strong energy condition. It's a fancy way of saying that you create energy from nowhere, right? So what they do is, okay, instead of doing this, I can still live with some comfortable dark energy zone, and then increase the N effect. That's also possible. Right.
how about denominator?
Here? Yeah. Then this one. Oh, this. Yeah, this. I think this N effective is also affecting denominator indirectly because that N effect increasing N effective it will add more relative degree of freedom that will change the expansion rate. Oh yeah, too. So N effective is going here and going there. Right. And then rest of this paper is about early dark energy, and as Changbom correctly pointed out, that's what they did exactly. So they want to, it's also someone's question, they want to make H naught bigger by adding some component early on. Right. So making this whole thing smaller. Right. If you make the denominator smaller and then you make the H naught bigger, how do you make it smaller? And you add something to the denominator of the integral. And that's what they did. So they add all the dark energy, and it's a little ad hoc, but when I complained, Mark told me that, yeah, what about this case that tomorrow Mother 7 company in IAS told us that, oh, there's some great reason to believe that there's dark energy early on. Then you can say that that's natural. That's redshift. The general all the dark energy concept is this. We have radiation that is proportional to 8 to negative 4. And we have matter proportional to 8 to negative 3. And lambda constant. So all the dark energy behaves like dark energy early on. Here, but then decay faster than the radiation. This has dark energy phase, and then decay fast. So you don't know. So in terms of the density parameter, so omega of dark energy, the early dark energy, it's negligible around this time. It rises and then falls, then negligible for the rest of the cosmolocation. About 0.1, and most 10% before CMB last scattering, because you want this to contribute here, right? Then you can see why it contributes this way, because it increased the denominator, therefore decreased the whole integral without touching anything else. Okay? But then they argue that, oh, it's not so trivial. I mean, it sounds easy, but it's not so trivial because if you are to add something very exotic, and you may think of you may have to think of the nonlinear dynamics of dark energy and blah. Yeah. But
So according to the integral,
Yeah.
there's no constraint on the epoch of this
no.
dark energy.
But then they didn't want to do it very far away, because then if they turn on very early on, and it'll also again screw up the higher order peaks. Because small scale CMB enter the horizon early on, and then experience all things that happen between the horizon entry until the last scattering. But they want this as close as possible to the last scattering.
They also affect the epoch of equality, matter radiation, because there's one more component.
But they decay, right? They decay faster than radiation.
So that goes to the constraint on the epoch of this dark energy.
Yes,
So
yes.
that has to be
Right.
hidden.
That's right.
before
Yes, yes,
that's the-
yes, yes. Otherwise, we will see that in the, say, early ISW effect. Yeah. And then they concluded with some suggestions of how we can test this idea. Many of them are theoretical, because one idea is that now we had one dark energy and one early dark energy that was motivated by string theory. They said, I don't know, don't ask me. String theory motivation, I was thinking of that. But then the reason is that the fact that we have one early dark energy means that there could be another dark energy phase. That's what they could search for. Because this is very weird. I mean, this is dark energy from some fundamental theory that happens that's operating in EV energy scale. I heard of.
So this dark energy decay to what?
Ask Mark. Yeah, I don't know. They didn't give some. Well, I think that their model is like a axion type model, so it decays as they oscillate around the minimum. They decay into. There's a friction term due to expansion. That's what stopped the field oscillation eventually. And I think one thing that I like about their future constraint check is, because I wrote the paper, is if we consider this modification of early expanding history, right? Then it will change the sound horizon, but it'll also change the light horizon, right? Because you change the distance that sound wave propagate, you also change the distance that light propagate. Now, can you see that? If we are lucky enough to detect a BB power spectrum in CMB, and BB power spectrum has rise and then fall, and then there's characteristic scale that is a light horizon. And if you modify the expanding history early on, then you must modify the BB spectrum peak position. That's what I wrote with Mark. He wrote that. Right, I think that's all in this paper. And I think the takeaway message perhaps is this equation. So if you're curious that if your new model of dark energy or new model of expanding of universe, if you're curious if that will solve the Hubble tension, that's the equation. You can simply integrate. Or if you are wondering, like the question that you asked, what if you combine these two, right? What you can do is you can start with a W-1 and an effective of canonical value. You change it little by little, and then see how this integral wind up changing. And then that's the way that we can plot what the Laila showed last week, right? That's the CMB part. And as you can already see from my enthusiasm, I like this measurement a lot better, because look at this error bar and then look at all these consistent features, and then we can explain what are the possible causes of curing this problem from the equations, not like calibration. So I think if I have to bet my money, I'll bet this is right. I don't know. This is my personal taste.
So this is written by Adam Reyes.
Yeah.
So he's suggesting how CMB can be wrong. Okay?
They didn't say that, because
they are not presenting how the local measurement can be wrong.
Right.
Okay. Whereas they show this and suggest people to fix one of these.
Right. Yeah.
Okay.
Also, Mark has the already documented theory. Yeah.
So that implies that they suspect something maybe can be improved by fixing one of these histories.
Right. And looking toward the future, though, I think one of the clean measurements that we can expect is gravitational waves. That's the local measurement is completely free from this acoustic physics, right? Then you can measure the luminosity distance from gravitational waves. And then if you can identify the redshift, then you can plot. You can have independent check of the Hubble constant measurement from the gravitational waves. That's the direction that I think I'm going. In fact, yeah, that's what NSF forced me to work on because they seem to fund me.
Okay, thank you very much. Great job.
Yeah, just one comment. I mean, what we're measuring is fluctuations in temperature. Okay? And from the angular power spectrum, we get that impressive number.
Yeah.
But that's in temperature. Now, when you're doing this equality, you're assuming two things. One is that fluctuations are adiabatic.
Sure.
Therefore, you're translating temperature fluctuation into density fluctuation. But if we believe in some variant of inflation, we know that we're going to also produce isocurvature fluctuations, entropy fluctuations. So the question is, Planck has constrained that very much to some perhaps 5% or less.
Very small, yeah.
Right?
4%.
But, so my point is, how much isocurvature fluctuations are allowed so that we can change that adiabatic nature? And the second is the denominator. You are putting the angular diameter distance there. But then you're assuming an homogeneous universe. And that's inconsistent with lambda CDM, which predicts a huge number of halos. And therefore, the N of sight will be highly inhomogeneous. Right? So both the numerator and the denominator have assumptions which are hidden.
Right, but then this deviation. Okay, there could be a deviation. Maybe I think that at this level, like this 0.5 kilometer per second per megaparsec, maybe we start to worry about this thing. But this deviation is not order unity, right? It's very subtle. Like isocurvature is like less than 4%, and it's not. I mean, anisotropy of angular diameter distance should be very small. I think it's less than 1.1% because CMB is uniform, right? We only see the dipole, which is like
that's the isotropy, not the homogeneity.
Yeah. Oh, I see. You mean that we could live in the void? Okay. Sure.
The inhomogeneous solutions will give you different dA.
Perhaps, yes. Okay, that's right. Yeah, I don't. Yeah, I think old days. I'm not so long. 10 years ago, I saw some papers claiming that the local Hubble volume and then supernova at the same time, but I didn't see those kind of analysis these days. So I'm not sure. People are fascinated about.
They become very constrained, right? They assume back in 2000 that we live in a local void.
Right.
And therefore, the acceleration was only due to the evolution of the void, right? But then that implies that we are very close to the center of the void, which otherwise would produce a dipole that we don't measure. And that goes against the Copernican principle.
Right.
So it is very constrained.
But this was, I think, constrained by the Stebbins. Albert wrote the paper that if you're at the very center of local void, we should see the KIAS effect, and that is not consistent.
But one thing is that they are constrained, another thing is that they don't play any role. Okay, and that perhaps we should explore a bit more.
Yeah, even though they're constrained, maybe there are some like small change there can lead. Yeah, that's possible.
So if there is an isocurvature component, the law of Z relation will change, and this 3 over 4 factor in R.
I think our isocurvature will do more on the perturbation, but I think as long as it doesn't contain some fluctuation in the scale, my hunch is that it will be relatively safe for the isocurvature, because it's very non-trivial to create like this. Normally isocurvature is like this, right?
That's right, but that will contribute to the height of the peak.
Yeah. Yeah. True. Yeah. That's right. I mean, again, at this level, this precise level, then maybe it's like we may want to, consider that.
I mean, this assumes that fluctuation is completely, 100% adiabatic.
That's true. Yes. Yeah, there are many alternatives that we can try. I mean, it's all because we have such a precise measurement, right? So that we can try those.
The only thing precise is theta S.
Well, look at that. 3 zeros and 1.
No, but also that assumes adiabatic filtration. Remember the old
Oh,
times,
true. Yes.
isometric
Yeah. That's right. Theta is the primary observable. That's right. Yeah. These are all derived. Maybe that's the thing that we can try. Yes. So how much variation of these omegas? I mean, omega B and omega N. Those are crucial here. It's allowed when we include adiabatic correlation. Maybe that's the thing that we can try.
More question? Let's. Okay. I really wanted. I mean, I haven't paid attention to H0 tension for a long time, and I recently got more interested in.
Right. Yeah.
As
Because of your
to
measurement, right?
pay his time to study.
It was fun. Yes, fun time to study.
But yeah, I think this is very interesting to know, and I'd like to thank Donghui for doing this.
Yeah,
Okay.
I've known this physics for a long time, but having written down this simply, when that actually makes difference, right?
Okay, let's thank Donghui. Let's have 5-minute break to